Yes, so working with algae to develop feedstock for fuels or chemicals is a great idea. So it's got great potential, and that's why my team works on it. It's one of our major research areas. Our research is really largely directed towards understanding the microorganisms and understanding the systems so that we can reduce the costs and make it more competitive so that we can eventually...
Hello, I'm Danny from KEN-Tech, and this is Dr. Bruce Rittmann, who is currently a director of the Swette Center for Environmental Biotechnology at Arizona State University. Thank you for being here, Dr. Rittmann.
My pleasure. Glad to be here, Danny.
So, a couple of ice-breaking questions first. Can you tell us a bit about your background and how you became interested in environmental biotechnology?
Sure. So I was an undergraduate student in the early 1970s. And in the early 1970s is when we, at least in the United States, became aware of a lot of big environmental problems that we had caused for ourselves. And in fact, the first Earth Day was in 1970. So when I was an undergraduate student, there was a lot of interest in the environment and doing things to improve our situation in the environment. So that's part of it. I was very motivated by the need for us to do something. Plus, I was an engineering student, so I was doing engineering, and after a few years, I got into environmental engineering, which is a part of the civil engineering program that deals with water and air and solid waste and other environmental challenges. So that's how I got into the environmental engineering field. Some years later, I decided to become a PhD student, and I applied to several universities, and I was very fortunate to be accepted to Stanford University, where I got to work with Professor Perry McCarty, who is, I would say, the grandfather of the field we now call environmental biotechnology. We didn't call it environmental biotechnology back then. We had other names, but that's what the field became. And I was so lucky to be able to work with Professor McCarty.
So I'm assuming that with all that rigorous work, you were finally able to get to where you are right now. As the role of director, what do you enjoy most about it? What are the advantages or perks of being the director of the Swette Center for Environmental Biotechnology at ASU?
Okay, well, there are two things that I really enjoy the most, and they're closely related to each other.
Okay.
Number one is I get to work with a lot of really smart, motivated people, most of them quite a bit younger than me, like graduate students and postdocs, and they're always stimulating me with new ideas. So the second reason that I really like being the director is I get all these new ideas that come to me, most of them coming from my students or my postdocs, and they share their ideas with me, and we then work together to develop the scientific and technological areas that we're pursuing now. So working with young people, helping them advance and getting their good ideas, that's the really fun of the job.
I guess as time progresses, you get more and more of these students that have better ideas, just kind of piling on top of each other.
Yes.
Yeah.
Well, I've had a lot of students over the years, and I try to encourage them to think creatively and share it with me. I'll share my experience with them.
Oh, that's nice. That's very nice. So here are a couple of research and knowledge questions based on the previous papers you participated in. Your paper published in 2023 using algae as an energy source has been quite influential. What might be the ideal way to use algae at not just a lab scale, but as an industrial scale energy source?
Yes, so working with algae to develop feedstock for fuels or chemicals is a great idea, because the algae, they take their energy from the sun, and they take CO2, which we can give them from the atmosphere or from, say, combustion sources, and they take then this problematic CO2 and they valorize it using the sunlight energy to make useful things. So it's got great potential, and that's why my team works on it. It's one of our major research areas. Now the challenge today is that producing these valuable feedstock for fuel or for chemicals is still too expensive. Yeah, we can't generate the microalgae and the products from the microalgae at a low enough cost to compete with fossil sources, petroleum and natural gas, for example. So our research is really largely directed towards understanding the microorganisms and understanding the systems so that we can reduce the costs and make it more competitive so that we can eventually replace all these fossil sources with this sustainable, carbon neutral, solar driven energy and chemical feedstock.
Okay, so I'm guessing that the key towards industrialization isn't more production, it's reducing the cost of the production.
It's reducing the cost, but to reduce the cost, we have to increase what we call the productivity.
Yeah.
So how do I define productivity? So you've got the sun, and you've got like a square meter of area which the sun is coming down. You want to get the most product out of that square meter and the sun that's coming on it. So we have to increase the productivity, the amount we get out, and that's how we decrease the costs and make it more competitive. So that's what we're all about, is increasing the productivity per unit area of sunlit land.
Here's another research question. Your research on hydrofluorinating perfluorooctanoic acid,
yes.
also known as PFOA. So this contributed to a lot of better methods of purification. Could you explain why PFOA is so dangerous and like some of the best methods of hydrodefluorination?
Yeah. Okay, so PFOA, that stands again for perfluorooctanoic acid. It's one of the most prominent of the molecules that we go into the broad class of PFAS, as per and polyfluorinated alkyl substances. There are thousands of these that have been produced over the years since the 1940s. They're used in all kinds of things. We're eliminating many of the uses, but they're used in like Teflon frying pans, and they're used in clothing. They're used in McDonald's hamburger wrappers. They're used in firefighting foams and in fire-resistant materials. So they're used everywhere, and because they're used everywhere, and of course they're manufactured, and things get released during the manufacturing, they're everywhere. We find them in waters and soils everywhere in the world. You can find them in Antarctica, for example. And of course, you find them in drinking water supplies, and they are ubiquitous. They're also what's known as the forever compounds, and that's because the carbon-fluorine bond, CF bond, is really difficult to break. And it's especially difficult to break in what we call perfluorinated compounds. Perfluorinated is a chemical term that means every location on the carbon chain that could have a fluorine attached has a fluorine attached. So the whole molecule is covered with fluorine, which means that every bond is really difficult to break. And I'm interested in biodegrading things, and the microorganisms just can't get a grip on the molecule because these fluorine atoms are everywhere on this. So that's why they're one reason they're a big problem. Of course, they have serious health impacts. They're implicated in cancer and heart disease and several other bad things that we don't want to have. So we are working to remove them from products. We're working to develop technologies to remove them from contaminated waters and soils. And that's where I come in. We're developing novel technologies to destroy these PFAS molecules in the water. So how do we do this? So I'm the director of the Center for Environmental Biotechnology, which means I like to use microorganisms to do these things. But these perfluoride compounds just are not biodegradable. And so we can't rely solely on the microorganisms to do the job. So what we're going to do is we're going to give them some help. And that's where hydrodefluorination comes in. And what we do here is we begin the process using chemical catalysts based on the metal palladium, and we deliver hydrogen gas, H2, hydrogen gas, that's the hydro part, to these catalysts, and then in contact with the water that contains the PFOA, and the hydrogen then breaks the carbon-fluorine bond by reducing it, and so you remove the fluorine and you substitute in its place a hydrogen. Now what we know, and we've shown in our research, is that if you remove only a few of those fluorines and substitute on hydrogen, now the molecule becomes biodegradable. And we let the microorganisms finish the job. So it's what we call a synergistic process. It's a synergy between the palladium-based catalytic hydrodefluorination, followed by then the microbial biodegradation to completely destroy the molecules. And this is really, really important because the technologies people use today when confronted with water contaminated by these PFAS molecules is to do what we call adsorption. That is, you remove it from the water and you put it onto a solid adsorbent, like activated carbon, which gets it out of the water but does not destroy the chemical. And so what we're doing instead is not absorbing it, but we're actually destroying the molecule. All the fluorines are removed, all the carbon is oxidized. It's completely harmless.
So instead of just implementing a biological method of degradation, you use a two-step method of degradation, first chemical and then biological.
That's right, and this is a common theme when you're dealing with these very difficult to biodegrade chemicals, and the fluorinated ones are the most difficult, but it also applies to chlorinated compounds and some other classes that are really hard to get the process started.
And I'm assuming there's also research being done with different kinds of metals,
Yes.
not just palladium.
Yes, we're looking at palladium as sort of the core metal, but we use other metals to complement the palladium.
Oh, okay.
Palladium isn't perfect, and we can add other metals and make its performance better over the wide range of conditions where we have to treat the water.
Okay, thank you.
Yes.
So moving on to practical applications and impact. Your work on bioremediation of various pollutants is highly regarded. What are the most promising advancements in this area currently?
Well, I think we were just talking about one, and that is linking the biodegradation with some other process that helps the microorganisms get started. And so it's really essential for the fluorinated compounds, but it's also important for some chlorinated compounds. It's important for some very complex organic structures where, again, the organisms just can't get what I call a grip on the molecule to start breaking it down. And so we do then use various, because I'll say chemistry-based methods to get the process started. So we have used, in other settings with other molecules, we've used photocatalysts. So you have light that shine on a photocatalyst, and that creates what we call free radicals. And those are extremely reactive, and they then start attacking it's hard to degrade organic molecules. It's the same principle. You do a few chemical attacks and the molecule then starts to become biodegradable.
Okay, so I guess the trend for these bioremediation methods is having a mix of physical, chemical, biological, not just the one-way
That's
method.
Right. That's right. And the general philosophy I use is that sometimes we have to give our friends, the microorganisms, some help.
Yeah.
And so now we're finding ways to help them get started.
I'm assuming that with all these microorganisms that you're dealing with, you found some of them particularly helpful when creating MECs or microbial electrochemical cells.
Yes.
So what are some key considerations when designing an MEC cell for optimal energy and chemical production from organic waste.
Okay, so let me first define what an MEC is, what a microbial electrochemical cell is. So it's a form of a fuel cell, where in any fuel cell you have two conductive solids. One's called the anode, the other one's called the cathode, and they're connected by electrical circuit. At the anode, some fuel is oxidized. Oxidized means the electrons are removed from the molecule. So at the cathode, we remove the electrons, we oxidize the chemical, and we put those electrons into the anode, into the conductive solid. And those electrons then move to the other conductive solid, the cathode, where those electrons are used to reduce something. And reduce means add electrons. So a common example would be taking oxygen and reducing it to form water. That would be a microbial fuel cell. Another one that we study a lot is to reduce protons, hydrogen ions, to produce hydrogen gas, renewable hydrogen gas that bubbles out of the solution, and we capture it. Now, in a microbial electrochemical cell, what's completely unique is that at the anode, the catalyst is a biofilm of bacteria. And they catalyze the oxidation of the fuel, some organic material, and then transfer those electrons into the anode to get the whole process started. So that's how it works. And so on the one hand, in a microbial electrochemical cell, you need to have the anode with these what we call anode respiring bacteria, the ones that oxidize the organic material, transfer the electrons to the anode. You need to have them present. And so we've studied, we as a field have studied those microorganisms for 20, 25 years now. We know quite a lot about the organisms and how they do their job. Now the electrons then go over to the cathode and they have to reduce something. I always said they could reduce water or they could reduce protons and they can reduce other things too. And there we need to, we need a very efficient process. The microorganisms that are really good working at the anode are ones that can oxidize organic material, but most importantly can do what we call extracellular electron transport. That is, they can remove the electrons from the organic material and then transport them over long distances, from the microorganism's point of view, long distances, to get to the anode without losing the electrons. Okay? And organisms get energy, we call that anode respiration, and they get energy from it, and so we need organisms that can do this. Fortunately, we've been studying these organisms for 20 to 25 years, and we now know that this characteristic of being able to do extracellular electron transport is not so rare. There are actually quite a few organisms that can do this very well. So we need to create the conditions at the anode where we select the right organisms, so the right ones are there, and they proliferate and accumulate. So that's the key thing is creating the conditions to get the right organisms. And this is one of the things we study. How do we do that? We have the electrical potential, the pH, and things like that that are really important. Now, the question that you didn't ask but is really important is, well, what about the cathode? It turns out in these microbial electrochemical cells that the weak link in terms of practical application is at the cathode. It's not the microorganisms. The microorganisms are really good at oxidizing organics and transferring the electrons to the anode. That's not the weak link. The weak link is at the cathode, where it's energetically expensive to transfer the electrons to reduce oxygen to water, or to reduce protons to hydrogen gas. And so there's where our problem lies, and that's what makes the system kind of slow and therefore too expensive. So this is where we need to be putting a lot more of our research efforts, is understanding the cathode and how to make it function a lot better.
So I'm guessing that's the reason why a lot of expensive metals are used for the cathode.
Sometimes, yes. So some of these metals are like platinum and things like that are used there because they are catalysts for these kind of electron transfers. But we prefer not to use them, and so we prefer to look at other conditions in the system to make it work more efficiently without having to pay for these very expensive metals.
Okay, so that's the end of the research-based hard questions. Future-focused questions for upcoming scientists. So what advice would you give to young scientists and engineers who are just starting their careers in environmental biotechnology?
Yeah. So environmental biotechnology is characterized by being really interdisciplinary. That is, to really be a good researcher or technologist, you have to understand the microbiology, but you have to understand the chemistry, you might have to understand the electrochemistry, and mass transport and other things like that that are really important. And so someone who gets into the field should understand that they have to broaden their knowledge, not focus it more, but broaden it on it. And that's different than in some fields from which the students might have come on that. And so students have to embrace interdisciplinary and wide-ranging knowledge on this. So that's number one. And number two, of course, is you have to do what we just talked about a few minutes ago, and that is understand that it's not the microorganisms all by themselves. We have to help the microorganisms. Microorganisms can do all kinds of wonderful things, but we sometimes have to give them some help. And it's not strictly biology that gives them the help. It's chemistry and catalysis and a few other things that are really, really important. And finally, the last thing I'm going to emphasize here is that what we do is quantitative. So this is a natural for most engineers. Most engineers get into their business and they like mathematics and they like solving equations and stuff. But that's not true because remember, for everyone, because a lot of people come in from other disciplines where that's not their strong suit. So no matter from where a student comes in, they have to embrace the quantification of it. So we know what's really important, what has a strong effect on the rates, what has interesting but no effect, and we don't pay as much attention to it. So interdisciplinary quantification, these are the key, and looking broadly at the things that the tools we have to make the system work well. Those are the keys.
So if I went into biology because I didn't like doing math, I'd be in a lot of trouble.
You would change your opinion.
Okay, thank you. So how do you envision the future of environmental biotechnology in the next 10 to 20 years?
Yeah, okay, there are a few driving forces. I mean, one driving force is the very rapid increase in the tools we have available to us, the tools from what we call the omics, the genomics, transcriptomics, proteomics, metabolomics, all the ones that allow us to understand at the molecular level what the organisms are doing and how they are doing it. So this is tremendously changing and expanding all the time. So we as researchers in the field need to keep up with this and embrace these new tools on it. So that's number one. Number two is we have a lot of potential to get help from what I call materials science or materials engineering. The catalysts and nanomaterials and things like this that are also really hot research areas. And so we need to embrace that we can get a lot of value from these other areas that are not our traditional area, but that can really help us to do a better job working with the microorganisms in our practical settings. So those are the two things. And then third, this is always true, one has to be creative. We're looking for creative solutions. You're not going to find the answers in the textbook. You're not going to find the answers even in most in papers. You have to think creatively about what you're doing and don't be afraid to do something totally different.
Okay, thank you very much. So finally, what do you consider your most significant contribution to the field, and why?
Well, I'm going to give you a two-part answer. Part one is I've had a lot of students and other researchers who've worked with me over the years. I've had more than 60 PhD graduates, and they all go off and do wonderful things. And so I think one of the great contributions I've been able to make is to help these people develop in the field and be successful. So I'm very proud of them, and I'm proud of my ability to have helped them advance on that. And the second thing is again making it clear how we can embrace this interdisciplinary thing, combining the biology, the omics with the engineering, with the materials. This is the integration part. This is what I do a lot of, and I really think this is the future, and it's the current and the future. So I think that's one of my great contributions is to really showing how we can integrate these things together.
Okay, thank you for your time.
Great, thank you, Danny. Glad to meet you. Glad to be here.
Thank you very much.
Thank you.